Okay. So take a look at this. It was so much writing and we're a little bit pressed for time, so I did put this on paper for you, and I know sometimes not as much happens, you know, like when there's a connection between writing it and it going to your brain, a little more happens than if you just read it. So let's try to read and discuss it together. Don't zone out on me, okay? Stay with me, participate. So we're talking about the Lagrange form of the remainder. It's also called Taylor's theorem. When a Taylor polynomial is used to approximate a function, we all know what those words mean, right? Take a polynomial, plug in a value, use that polynomial to approximate the actual value. We need a way to see how accurately the polynomial approximates the function. Well, if you think about it, if you take the actual function, f of x, and you subtract from it whatever degree polynomial you went to, whatever is left over would be your remainder. Right? That makes sense to everybody? So whatever's left over, once you stop, that's your remainder. That would be the error associated with your Taylor polynomial approximation. So here's what Taylor's theorem said, or says. All right? If we've got a function and it's differentiable through the order n plus 1, meaning if I stop at the nth degree polynomial, I can take one more derivative, okay? In an interval containing c, what's c in all this? The center, right? It's where I have centered my polynomial. Then for each x in the interval, there exists a number z between x and c, okay? X is the value that I'm interested in approximating, right? C is the center. So in that problem that was up over there in the corner, the center was 2 and the x value was 5/2, right? In that last problem that we did together. So we're saying there's a number between those two values such that, here's the actual function, here's its Taylor polynomial approximation, right there, and there's that remainder that we're talking about. So this z exists between x and c, where the remainder or the error is this. It is less than or equal to, what does this represent? The next term. And what is that word right there? Max. So what I'm doing is I am considering the next term, but instead of just the next derivative, I need it to be the max the next derivative could be on that interval between x and c. Okay, whatever the maximum derivative from x to c is what will be multiplied by the next piece of the Taylor polynomial. Okay? So here's what's going to happen. In problems, they're either going to give you the max the next derivative can be, and we like that, okay? And that seems to be the trend that APs move toward, is that they tell you the max the next derivative can be, or we have to actually figure it out, okay? So 2 ways of figuring it out. The other thing we could hope for is that they give me sine or cosine. What's the max sine or cosine can be? 1. Okay, so that's the max derivative. If you got sine or cosine, even if it's outside the interval, the max the derivative could be is 1, and you're looking for a max error bound. Okay, so we're good with trig functions, and we really like it if they tell us the max the next derivative can be. The other way that you may have to do it is use your calculator and look at the derivative from x to c and see where or which value has, I know it sounds like I'm saying ecstasy. See what the greatest derivative is on that interval. Okay, so we're going to examine the other 2 types today. All right, so this just talks about Lagrange and that. Okay, so let's go look at example 1 down here. All right, are you with me conceptually, like big picture wise? Got a polynomial, have error associated with it, and that error has to be less than or equal to the max the next derivative can be of the next term in the series. Okay? So very similar to alternating, right? We're talking about the next term, but it's the max the derivative can be there. Okay, so here we go. Let's look at example 1 together. Let f be a function with 5 derivatives on the interval 2 to 2.7. Assume that what does this mean? The fifth derivative. Okay, assume that the fifth derivative has to be less than or equal to 0.2 for all x in the interval 2 to 2.7, and that a fourth degree Taylor polynomial for f at c is used to estimate f of 2.7. Let's put some symbols down that represents that sentence, because that can be a little overwhelming, right? So f of 2.7 is being approximated by what? The fourth degree Taylor polynomial, right? It's being estimated by the fourth degree Taylor polynomial, and to this would be added the remainder associated with that fourth degree polynomial. Okay, and that would just be f. So f of 2.7, I can actually put those values in here, is the fourth degree polynomial at 2.7 plus the remainder associated with that fourth degree polynomial when x is 2.7. So x is 2.7, what's c? C is 2, right? C is 2. Okay, this remainder right here, the fourth degree remainder at 2.7 must be, its absolute value, must be less than or equal to what? The max, the fifth derivative at z. And where does z lie in between again? X and c. Times what?
X minus c, so x minus 2.
X minus 2
To the fifth.
divided by 5 factorial, right? And notice we have absolute value bars here. We don't want negative stuff. Okay, so once again, the remainder associated with the fourth degree polynomial at 2.7 must be less than or equal to, what did they give you in the problem? The maximum the fifth derivative could be, right? We like this problem. So what goes in here? 0.2 times what gets plugged in for x? 2.7 minus 2 to the fifth power over 5 factorial. Which is less than or equal to, has anybody calculated that? Has anybody with a calculator out? I'll give you this one. You guys can get your calculators out. Okay? All of that comes out to be 0.00028. Okay, so what is this again? This is the max error, what? Associated with, very good, associated with the fourth degree polynomial at 2.7. Make sense? It does, I think. Okay, so that was all of part A. Part B says, suppose, what does this mean?
The actual value. The value of fourth degree polynomial.
The value of the fourth degree Taylor polynomial at 2.7 is 1.763. Use your answer in A to find an interval on which f of 2.7 must lie. Okay, so the fourth degree polynomial at 2.7 we said is 1.763. So f of 2.7, which is the actual value, must lie where?
Between 1.763 minus 0.00028 and plus.
Absolutely. Between 1.763 minus 0.00028 and 1.763 plus 0.0028. Does that make sense? So the actual value has to lie between 1.76272 and 1.76328. So part C and D should be really easy to answer. C says, could f of 2.7 equal 1.7621? No, why not? It's too small, right? It's not in that interval. D, could f of 2.7 equal 1.7631? Yes, because it is right in, it's in that interval, right? So this one, no, yes, not an interval, an interval. What do you think? Yeah? Okay, let me see how far I can get into example 2. Okay, example 2. Find the fifth degree Maclaurin polynomial P sub 5 of x for f of x equals sine x. We all ought to be able to produce that pretty darn quick. Right? Sine of x, fifth degree polynomial would be equal to what? X minus x cubed over 3 factorial plus x to the fifth over 5 factorial. Sweet. Then use your polynomial to approximate sine of 1.45. What does that mean to do? Plug 1.45 in for x, right? So sine of 1.45 will be approximately equal to, right, the Taylor polynomial at 1.45, which is 1.45 minus 1.45 cubed over 3 factorial plus 1.45 to the fifth over 5 factorial. In the interest of time, I will give you that answer. 0.995. Okay, so we wrote the polynomial, we approximated sine of 1.5, and used Taylor's theorem to find the max error for your approximation. Okay, so if this is the fifth degree polynomial, I need to talk about the fifth degree remainder, right? So the remainder associated with the fifth degree polynomial at 1.45 has to be less than or equal to what? The max the derivative of, it would be f, it would be the sixth derivative at z times, this is Maclaurin, right? So my center is 0. So what value goes in here? X, which is 1.45 to the sixth divided by 6 factorial. So that remainder, we're dealing with the sine function, right? What's the max the derivative of sine can be ever? 1. So I can replace that with a 1. And this comes out to be 0.0129. So the max error has to be less than or equal to 0.0129. So yeah, that's part A. So what does part B say, just really quickly? What does it say to do? Find the interval, right, on which it must lie. So I should take 0.995 and subtract 0.0129, right? And then add it over here. And that is the interval on which it must lie. Okay, does that make sense to you? Okay, so for homework, here's what I want you to do. You can finish example 2. I want you to do example 4. And then on the homework, I want you to do 1 and 3. Okay, 1 and 3. And you do have answers in the packet. Okay, so finish example 2, complete example 4,